Have a good day, everyone. Before starting on my presentation, I would like to thank the organization and scientific committee to give me a chance. And first of all, I would like to introduce myself. I'm from University of Selçuk, Turkey, and I conduct my research activities in the same university. Today I'm going to talk about the recent advancements about graphene-based aerogels and impact of the drying processes on the physical properties of these materials. And in my presentation, I would like to give some brief introduction about the graphene-based aerogels and supercritical drying method, freeze drying method, and characterization, results and discussion part, and I am trying to conclude my presentation. Yes, the graphene oxide materials has attracted great attention due to its excellent features as adsorbent of metal ions, organic pollutants, and because of the large amount of oxygen atoms on their surface in form of epoxy, hydroxyl, and carboxyl groups. However, the graphene oxide can be readily diffused into water and difficult to separate and reused, which may cause the treated water to be repolluted. And it is more appropriate to immobilize graphene oxide material in porous biodegradable materials like sponge for wastewater treatment, especially the wastewater containing micro and nanoplastics. Due to fascinating properties such as low density and theoretically about 160 gram per meter cube, and chemical inertness, high mechanical properties, abundant interconnected porous framework, and high specific surface area. And I will tell you it depends on the drying methods. Graphene aerogel has been considered. Yes, and the graphene aerogel is a three-dimensional nanomaterial that consists of many two-dimensional graphene sheets that can be lighter than the air. As you see in the picture, the, this material is so lightweight, and different nomenclature is used depending on the drying process of this material. In the first step, the solution of precursor salt formulation, and then gelation process, wet gel, and the drying process is integrated to the system, such as supercritical drying, atmospheric drying, and freeze drying. And in these systems, we are using and comparing the supercritical drying and freeze drying systems. Yes, as you see the phase diagram of the carbon dioxide and the water, visualize the various phases such as solid and liquid and gas phase depending on pressure and the temperature. As you see, the phase diagrams of freeze drying and supercritical drying and superposed on water and carbon dioxide, respectively. The carbon dioxide as at 30 1.1 centigrade degrees and 73.8 bar is in its supercritical state, in which there is no distinction between the liquid and gaseous phases. As you see, the same as these critical values for the water. Yes, supercritical drying generally yields aerosols which have higher pore volumes and porosities, higher surface areas when compared to freeze drying and ambient pressure drying. Yes. What about our characterization technique? In our study, we have utilized these characterization techniques such as PET to measure the surface area and SEM microscope, scanning electron microscope for the morphological analysis, and Fourier transform infrared for the structural analysis of the materials. Yes, the microstructural characterization, the obtained supercritical dried graphene aerogel, as you see on the left, and the freeze-dried graphene aerogel on the right, samples present many randomly distributed pores with wrinkled texture in Figure 1, and the sample appeared to have a well-organized and fine pore structure after being dried in supercritical media. Yeah. And using the Brunier-Emmentaler abbreviated BET method, the surface areas of supercritical dried graphene aerogel and freeze-dried graphene aerogel samples were determined because of the layering or overlaying of graphene sheets. The graphene aerogel surface area was significantly less than 2,600 meter square over gram, which is the predicted value for a single graphene sheet. The surface area of the supercritical dried and freeze-dried graphene aerogel at approximately 330 and 70 meter square per gram respectively. This result showed that the surface area of aerogel dried in supercritical media is about 5 times higher than freeze-dried aerogel. Another figures show that the Fourier transform infrared spectra of the supercritical and freeze-dried graphene aerogel samples on the left-hand side supercritical and right-hand side the freeze-dried one. Graphene oxide usually exhibits a broad band at about 3,300 centimeter minus 1, which comes from the oxygen and hydrogen stretching vibration in the carbon hydroxyl groups. After all drying steps, the resulting 3D graphene aerogels almost have no bands in this section. Yes. And as a conclusion, the graphene aerogels were prepared by the social method and then dried either supercritical and freeze drying methods. And the drying method has a significant influence on the graphene aerogel's physical properties. The specific surface area of graphene aerogel obtained by two different drying methods differs significantly. Compared to freeze-dried aerogel, the surface area of aerogel dried in supercritical medium is roughly 5 times larger. The structural and morphological structure of graphene aerogel obtained by two different drying methods is similar. It can be concluded that the graphene aerogels dried in supercritical environment should be preferred, especially in applications where the advantage of large surface area is prominent, such as energy storage and environmental applications. And thank you so much for listening me.